Hi everyone, Miss Angel here. I hope everybody is having a wonderful day. This video is all about Unit 2, Lesson 2 for 8th grade math and the real number system. If you don't have your notebook or at least a piece of paper, I encourage you to go get one because not only so you can take notes during the video, but also so you can take notes throughout your whole lesson. Okay? So your lesson today is all about the real number system. Alright? The real number system is broken up into two major categories. There are rational numbers, okay, that's one of the major categories, and then there's also irrational numbers. Alright, so before we start, let's talk a little bit about a concept that you learned in 7th grade. Let's jog our memories for a minute, and let's talk about rational numbers. So the definition of rational number is a number in the form of a over b, or like a fraction, right? Where a is an integer and b is a non-zero integer. Okay, so what that means is that this can be an integer except for 0. You can't put 0 in the bottom of a fraction, right? Because if you remember, the denominator in the fraction, that's the bottom number, right? That tells us how many pieces something is broken up into. Okay, and you can't break something up into 0 groups, right? The smallest number of groups you could have would be 1, right? If I have 20 Skittles, I could have one whole group of Skittles, all 20 of them, but I can't have less than that. I can't have 0 groups, all right? So that's what that's referring to. So rational numbers are any number that can be represented as a fraction. Irrational numbers are numbers that cannot be represented as a fraction using integers. Okay? So we can talk about them first. Irrational numbers. The most common one that you've probably heard of is this number here, pi. Alright? That's the symbol for it. And the nice thing about having a symbol for it is that, because it goes on forever without a pattern, so there's not really a way for us to write the entire thing down. You probably have heard of the first few numbers, 3.14, right? That's a pretty common thing for people to know. But it does technically go on forever and ever and ever. All right? Here's some other examples. The square root of 2, the square root of 6, negative square root 17, right? If we were to even just enter those into a calculator, it would go on forever. All right? We wouldn't be able to see the entire thing. Rational numbers, and these are the numbers that we're going to see most often, are broken up into 4 major groups. All right, I'm going to start with the most detailed, I guess, is how we could say it, and that's right here, natural numbers. All right, natural numbers, those are also known as counting numbers. Those are the first numbers that you ever learned when you began learning math, right? Counting as just a little kiddo, right? 1, 2, 3, 4, and so on, right? Whole numbers include all of the natural numbers. That's why this box is inside of the whole number box. Okay? Whole numbers include all of the natural numbers, so notice I have them repeated right here, but it also includes 0. Alright? And then we get up into integers. So integers includes all of the natural numbers, all of the whole numbers, but then we also include negatives. So here's some examples. These are not all of them, right? It's just some. Negative 17, negative 2, there's that 0 again, 7, 18, right? Anything like that, okay? Then we get a little bit broader into rational numbers, right? And that's where that definition came into play, where they could be represented as as a fraction. All right, so some examples, we've got 12 25ths, 3 eighths, 45 100ths, negative 3 and 56 hundredths, negative 12 and 9 tenths, right? So we've got all numbers like that, but then it also includes the integers. It also includes the whole numbers and the natural numbers, okay? So the number 1, let's just take the number 1, right? Everybody knows the number 1. The number 1 is a natural number. It is a whole number. It is an integer, and it is a rational number. Some of you might be wondering, well, how do I write 1 as a fraction? You put it over 1. Right? If you have 1, and it's out of one group, or it's cut into one piece, right? then you'd put it over 1. So 1 over 1, or 2 over 1, 3 over 1, and that's how you'd write those as fractions. Okay, so let's go through. I have 3 problems for you. A couple of them are modeled after problems from your practice, which is on page 17 of your lesson. And then the final question is actually almost identical to one from your quick check. So it's definitely going to benefit you to write them down. The first one I've got here says, which number listed is an integer but does not belong in the subsets of integers? Okay, and actually let me get that other page back open. Okay, so let's think about this. First off, they're all integers. All right, negative 17, 0, and 17. Okay, so if they're all integers, right, we've got negative 17 and 0. I already even have those on my chart. Look at that, right? We could add the number 17 on there as well. So now we have all 3, right? But only one of those cannot be put into the whole number category nor the natural numbers category. Okay? So let's look at the first one that was on the problem, right? Negative 17. Can that be a whole number? No, right? Because whole numbers, they're all positive. Okay, so that right there, that tells us that one can't be a whole number. And if it can't be a whole number, it definitely can't be a natural number, because natural numbers are part of the whole number category. So 17 is a great option. All right, I have a feeling that might be our answer. But good mathematicians always check all of the options. So let's look at 0. Can 0 be an integer? Yes. Could it be a whole number? Oh, there it is. Yeah, that's a subset of integers. So right there, because it can be a whole number, that means it's not our answer, right? Because the question said, which number listed is an integer but does not belong in the subsets of integers? So because this is a whole number, it's not our answer. So, meh. Okay. How about 17? Well, there it is. We have it as our integer. But that's technically a whole number too, right? Because it's a positive number. It's also a natural number because it's one of the counting numbers, right? If I were to continue my list, I could get to 17 and that would be included. So because it goes into those subsets, that can't be our answer either. Okay? All right. Moving on. Number 2. And this is another one based off of your practice on page 17 of your lesson. 4 square gardens have the following areas in square meters. Which area has a rational number of meters as the side length? So this is another one that I was like, oh, it's kind of confusing. It's like the wording on it, right? So there's a few things we need to know. One, it says there are 4 of them. 1, 2, 3, 4. Cool. Got that taken care of. It also tells me that they are squares. Well, what do we know about squares, right? We know that squares all have the same side length. So that side is congruent to that side, which is congruent to that side. And that one, right? Those little tick marks means they are congruent, which is a fancy word of saying the same. Okay? So now we know that, right? We know that they are squares. All right? And these are their areas. Well, then we have to think to ourselves, okay, well, how do I find the area of a square? Well, look at all this prior knowledge we need. Area is equal to length times width. Well, with a square, those are the same, right? That's what we just talked about. The length and the width, they're identical. So what that tells me is that, like, let's say the length is equal to A. Okay, that means the width also needs to be equal to A, which also gives me something called a perfect square. right? You probably heard that term. And in 7th grade, you probably learned a little bit about exponents, right? So we could call this a squared too. There's like, that takes it a whole nother step up. Well, we've already been given this style of number up here. We've already been given those, right? So what we need to think to ourselves is, okay, well, which one of these numbers could I take a square root of, right? Because to find the square root of a squared number, there's that symbol right there. Those cancel each other out, okay? And that would bring us back to finding a, or the length of the square. So what we need to do is we need to find the square root of each of these. And you might be thinking to yourself, oh my goodness, Miss Angel, you just introduced so many concepts, you're stressing me out. That's okay. We're going to get there with all of this stuff, right? And hopefully a lot of this you learned in 7th grade, but we're also going to learn a lot about square roots and exponents this year. Okay? So with this, and you might even want to pull out a calculator, or you could look at a list of perfect squares. Look up a list of perfect squares. That's okay. Hopefully you'll be able to see my calculator. Oh, it's a little blurry. But I'm going to, there's a square root button. That's this one right here. Okay. So I'm going to type, let me try focusing this a little bit. Maybe that'll help. I'm going to type in the first one, 36. 36, and I want the square root of that. And I'm going to hit equals. Oh, 6. Right there, look at that. So what that tells me is like 6 times 6 gets me to 36. Well, let's see, can we do that same thing and get a rational number as our answer? Okay, so let me clear that. Let's do, what was our next one? 33. 33 square root equals, oh my goodness, look at that. That is not a rational number, okay? That is an irrational number. Look, it goes on forever and there's no pattern. It would continue if my calculator were bigger, okay? So this one, it would be about 5.74, but we know that's not even the right one, right? Times itself. All right. How about 75? Can we get a rational number as our answer with 75? Nope, that's not a rational number either, okay? So, that can't be our answer. 33 wasn't our answer. How about 250? Got 250 square root equals, 15.8 something under that, right? Not the rational number we're looking for. All right? So that's this one here. That means this was our final answer because it asked which area has a rational number of meters as the side length. 6. 6 is our rational number. Okay? It's also an integer. It's also a whole number. It's also a natural number. All right? So I know I threw a lot of information at you there, but in order for you to understand the problem, all these different concepts have to be in our brains. Okay? So, last one, and then you can go get to your lesson. Number 3, and this is actually taken from your quick check. So write it down. Write it down, okay? Because it's an answer on your quick check. A cube has an edge length, A, right? So here's my cube, edge length A. If it's a cube, that means every edge length is the same, right? It's basically like squares stuck together. So if this one is A, that means this one is A, and so is that one. A cube has an edge length A that is a rational number of centimeters. Identify which measurement will require the use of irrational numbers. Okay, so all of those are A, all of them are rational. We're looking for the one that involves irrational numbers. Okay, so again, just like the last problem, some of your background knowledge from 7th grade has to come back into play. One of those being volume. How do you find the volume of a cube? Well, that equals the length times the width times the height. I have all of those values. They're all A. Here's my length, here's my width, here's my height. And those are all rational numbers. So it can't be answer A. B, a diagonal of one of the faces. That one's a little different. A diagonal, let me get a different color. A diagonal would be like from this corner to this corner. There's the diagonal. Okay, so I'm not quite sure yet on those, right? But to find that, I can't just use A. I'm going to need a little bit more information. Okay, so I'm not sure on B yet. I'm not going to cross that one out yet. C, though, area of one face. So that's like the front of the cube, right? One of those squares. We talked about that in the last problem. Area is equal to length times width, or base times height. You could also say that. Well, that's just A times A. Those are rational numbers, so that doesn't require irrational numbers. Okay? So it can't be C. We're looking for which one could involve irrational numbers. And then D. D is surface area of the cube. Well, surface area, all I need to know is the length of A for that, and those are all rational numbers. So the formula for that could be, let's see, we'll just call it surface area. Well, the area of one of the faces was length times width, so we could say length times width. How many faces are on a cube? Well, there's, I gotta find my camera. There's the front, there's the back, there's the right side, the left side, the top, and the bottom. 6 faces. So I could take this amount and multiply it by 6. Those are all rational numbers, okay? So that can't be the answer either. So that leaves us with our answer of B. Okay? So I know that was a lot of information, but in order to get these correct and to understand and really have a complete understanding of all of this, we got to know how they interact with each other. So I hope that helps. I know that was a long video, but hang in there and call me if you need anything. Okay? Bye.